Infiltration is usually measured using flooding-type infiltrometer. The data collected are related to the variation of infiltration capacity over time. A simple infiltrometer is an example of such device. It is a 600 mm height cylindrical metallic ring with a diameter of 300 mm. The ring is first inserted into the ground to a depth of 500 mm. Then, water is poured into the top part to a depth of 50 mm. Before we proceed, we need to mark the top water level. Throughout the infiltration process, water is added at certain time intervals to maintain the water level. During this process, we need to monitor the volume of water added and the time passed from the last addition. The infiltration capacity of soil equals to the division of volume of water added by the time interval. The measurement can be ended when the infiltration capacity remains the same. One drawback of the simple infiltrometer is the tendency of infiltrated water to spread outside the footprint of the device. As a result, the actual area where infiltration takes place is larger than the area of ring. To overcome this problem, double ring infiltrometer may be deployed. Outside the 300 mm ring, we add one more concentric ring with a diameter of 600 mm. The height of both rings should be at least 250 mm. The rings are inserted to a depth where the height of protrusion from ground surface is only 100 mm. Water is poured to the depth of 50 mm in both rings. The remaining steps should be the same. The measurement for infiltration capacity is solely based on the inner ring. Water infiltrated from outer ring provides water jacket that prevents water infiltrated from the inner ring to spread outward. Thus, the inner ring tube area would equal to the infiltrating area. Infiltration capacity typically reduces exponentially with time. The value of infiltration capacity that remains constant near the end of measurement is also known as final steady-state infiltration capacity (FC). From this dataset, we can plot the mass curve of infiltration, which is basically the curve of cumulative infiltration capacity against time. Various models have been developed to describe the variation of infiltration capacity and ease its application in hydrological study. The first and one of the most popular models is Horton's equation. This equation expresses the variation of infiltration capacity as an exponential decay. To use this equation, we need to know the initial infiltration capacity F0 at the time when T is 0. Note that this parameter is not measurable from our experiment. Next, we need FC, and we already know it can be determined from the graph of infiltration capacity against time. Lastly, we need Horton's decay coefficient KH. This parameter is dependent of the soil properties and surface cover, and therefore it is quite difficult to determine its exact value. To evaluate these parameters conveniently, we need to take another approach. Given a set of data obtained from infiltrometer, we can plot the graph of ln Fp minus Fc against time and find the best fit line. The gradient of that line would be our negative KH, while the vertical axis intercept is ln F0 minus Fc. With a little calculation, we can then define the value of F0. Next, we have Phillips' model. The infiltration capacity is a function of sorptivity S and Darcy's hydraulic conductivity K. Again, both parameters are better off being evaluated by plotting the graph of infiltration capacity against time t to the power of negative 0.5. The gradient and intercept of the best fit line are S/2 and K respectively. Kostiakov model introduces local parameter A and B in the infiltration capacity equation. the value of A is always positive, while the value of B should lie between 0 and 1. To evaluate the parameters, we may work based on the equation for cumulative infiltration capacity. From there, we plot a graph of natural log of cumulative infiltration capacity against time. The best fit line should give a gradient of B and intercept of ln A. Green-Ampt model uses parameters M and N to represent the soil porosity, capillary suction at wetting front, and Darcy's hydraulic conductivity. We use the graph of infiltration capacity against the inverse of cumulative infiltration capacity to determine the best fit line intercept M and gradient N. Now, let's implement these models and work on dataset obtained from the infiltrometer. All we need to do next is to evaluate the model parameters based on the dataset. For Horton's model, we need to determine Fc from the table, and it equals to 21.6 mm per hour. Then, we calculate Fp minus Fc and then apply natural log on it. At this point, we are good to proceed with graph plotting. The intercept and gradient of best fit line are 5.147 and -1.807 respectively. As a result, the value of F0 would be 193.57 mm per hour. From here, we can write the final form of our Horton's equation. When dealing with Phillips' equation, we need to calculate t to the power of -0.5. Based on the best fit line equation, the gradient, namely S/2 equals to 69.668, while the intercept K is -21.634. As for Kostiakov model, we need to apply natural log to both cumulative infiltration capacity and time. From the best fit line, ln A is 4.434 and B is 0.573. The infiltration capacity would be 48.29 times t to the power of -0.427. Green-Ampt equation requires us to determine the inverse of cumulative infiltration capacity before we can plot any graph. Only then, we can plot best fit line out of it and use M of 2.671 and N of 4091.9. All four models that describe the infiltration data are now ready. Let us now try to estimate the infiltration capacity when time t equals to 100 minutes. To use these equations, we need to express time in hour, and this leads to the conversion of 100 minutes into 1.67 hour. Then, we simply substitute this value into the equations. The estimations from Horton's, Phillips, and Kostiakov equations are 30.06, 32.33, and 38.82 mm per hour respectively. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.